Hello, everybody. My name is Wolf Geppert. I'm the chair of the European Astrobiology Institute, and it's my great pleasure to welcome Kevin Heng to this edition of the seminar of the European Astrobiology Institute. Kevin Heng did his PhD at the University of Colorado at Boulder in astrophysics, and then went after some other appointments as a Zwicky Prize Fellow to the Federal Institute of Technology of Zurich in 2010. And in 2013, he became a tenure track assistant professor at the University of Bern, at which he was promoted in 2015 to professor. He will then next year move as a chair professor of theoretical astrophysics of extrasolar planets to the Ludwig Maximilian University of Munich in Germany. I am looking very much forward to this talk and would like therefore to give the word to Kevin. Kevin, welcome here, and the floor is yours.
So, thank you very much for having me. If you have questions or the sound is not clear at any point or something goes wrong, just interrupt me or tell the host, please. So I would like to, rather than give an overview of everything we do in my research group, I would actually like to talk about one specific problem. And this is one paper that just came out not too long ago, at the end of August, in Nature Astronomy. This paper is the approximate but general solution to a mathematical problem in classical astronomy that was posed about 105 years ago. So I hope by the end of the talk, you will understand what approximate and general mean. And you also understand why this is relevant to data analysis in exoplanet astronomy. So the background is that exoplanets are planets orbiting other stars. I don't think I need to tell anyone that on this call. Exoplanet detection is now routine, so routine we had a Nobel Prize for it 2 years ago. The next frontier on everyone's mind is the detailed characterization of exoplanet atmospheres. And the reason why we are interested in atmospheres is because if you cannot travel to these exoplanets, then beyond measuring just mass and radius, the spectra of these atmospheres is the only way to actually say something about the atmospheric chemistry of exoplanets. So all questions that are more sophisticated than just mass and radius have to somehow go through the chemistry of these atmospheres. So you can think of exoplanet atmospheres and their spectra and the inferred chemistry as a tool that you want to use to answer questions. And I think the questions that we would like to answer can be broadly categorized into two classes. There's the whole class of how they form, what their formation history is. This is the planet formation crowd. So they would like to use atmospheric chemistry to answer these questions. Then there's the so-called habitability crowd, which I think most of the people who are associated with the European Astrobiology Institute belong to. And questions of habitability and biosignature gases and so on must also pass through the atmosphere of the exoplanet unless you can send a probe to it. So, however, in order to interpret these spectra from these atmospheres, we have to overcome two technical obstacles that are quite important. The first is that you have parameter degeneracies in your interpretation of spectra. This is something you live with, you cannot get rid of it, meaning that different combinations of values of parameters produce the same spectrum. So that means that instead of giving one single answer for, say, the abundance of water, you get a probability distribution of answers that depend on the probability distributions of other parameters. The second is that, of course, there's always incomplete understanding of physics or chemistry. And in some cases, number one and number two are linked together. And one of these central problems, I would say, in not just in exoplanet atmospheres, but which permeates many branches of physics and science in general, is the long-standing problem of cloud or haze or aerosol formation. right? So I would claim that this permeates branches of physics such as climate science, planetary science, planet formation, brown dwarfs, and exoplanet atmospheres. So in a nutshell, basically our incomplete understanding of how macroscopic structures form or behave um, comes from our incomplete understanding of how they are formed from or influenced by microscopic particles. So in climate science, for example, one of the key questions is how do you form water clouds in a way that you can put into your models so that they are predictive. This is a hard problem. In the solar system as well, for example, how water would exist on the surface of early Mars is also a question of how CO2 ice clouds reflect infrared radiation or not back towards the surface. So the so-called scattering greenhouse effect. So your calculations for the scattering greenhouse effect depends on how you treat the scattering of radiation by small particles, so aerosols. Planet formation is very much about how to form the embryos of planets from little things like pebbles and planetesimals and so on. And this problem has been around for decades. It's a hard problem. In brown dwarfs, there's this problem called the LT transition. So how do dusty, cloudy L dwarfs transition into cloud-free T dwarfs? And this LT transition has also been studied for decades. And one of the key aspects of this problem is understanding how aerosols or clouds or condensates behave in the atmospheres of these brown dwarfs. And unsurprisingly, these challenges carry over to exoplanet atmospheres. And in exoplanet atmospheres, our ability to, for example, extract water or methane or carbon dioxide from the spectrum of exoplanet atmospheres depends on our ability to model the clouds and condensates. So this is a hard problem in general. So today I'm not going to give you the answer to this problem. That's way too ambitious. But I want to give you a tool that I think can move the needle forward on this problem, can possibly allow us to interpret data in such a way that we can gain some understanding and know where to look. And this comes in the form of actually two papers. So I said one at the beginning, but it's really two. So the first paper published in Nature Astronomy describes the new theory we found, the new theoretical solutions. It also shows you a demonstration of the power of these solutions towards Kepler data of an exoplanet called Kepler-7b. The second paper uses these solutions to interpret Cassini data of Jupiter that has been around since the early 2000s. So both of these studies collectively demonstrate that the fundamental properties of clouds, hazels, and aerosols may actually be retrieved from precise photometry alone. If you're exoplanet scientist, this is a radical statement because most people, when they think of clouds and hazels or aerosols, they think of spectroscopy. The first paper derived closed form ab initio solutions of reflected light phase curves. You will hear what this means. And this is the first time since Lambert in the 18th century and Hapke in 1981 that such closed form solutions that you can write on paper can be found. The reason why these solutions are important is because they're ab initio, so from first principles. So meaning they have no tuning parameters. And because you have no tuning parameters, it means that you have a chance of extracting what we think are fundamental parameters from data. So I would like to, the talk is structured into a few parts. I would like to take you first on a tour of the observations. Then I would like to take you on a tour of the theory, but also the history of the theory, not just the theory. And I'll tell you the theoretical result without actually bothering you with the mathematics. And then in the last part of the talk, I will focus on the implications for interpreting observations. So as I said, this problem is very old, and it goes back at least a century. And one of the oldest papers I found is this 1861 paper by George Bourne. So interesting paper, and during an interesting time when papers were written in a very different way from currently. And the paper claims many things, but one of the things it claims is that the albedo of Jupiter is 96.7%. it's actually not clear what albedo George Bourne is referring to. And I will show you in a few slides down that there are actually many different types of albedos. We now know that the so-called Bourne albedo of Jupiter, which is the amount of light reflected over all angles and all wavelengths, is roughly 50%. I'll show you modern data of that. So this paper, even though none of the numbers stood the test of time, was influential and led to the coining of the term Bourne albedo. The next paper was that I thought was important in my reading of the problem was a 1916 paper by the Princeton astronomer Henry Norris Russell. And in this paper, he considered a quantity known as the phase integral, which I will define in a few slides down. It doesn't matter what it is. At the moment, it just matters that this is something you can measure. And in very idealized cases, you can compute it as well. So if you assume so-called classic reflection laws, of which I will explain two in the talk, the law of Lambert and the law of Seeliger, you can compute what this phase integral actually is. And it turns out that these do not describe real planets or moons very well. It doesn't describe Venus, the moon, or Mercury very well. The third historical paper that I should mention, because this is very this body of work by Bruce Hapke is very important, because Bruce Hapke was one of the pioneers in studying the so-called phase curves of the moon. So he studied how the light of the moon is modulated as it shows different phases to the observer. This is why it's called a phase curve. And in fact, this body of work was influential enough that the parameters describing the function to fit the shape of these phase curves are called Hapke parameters. And I will mention Hapke's work again because it has been very influential in my thinking of this problem. So I promise you that I will talk about reflection laws. So here's the reflection law of Lambert, sometimes known as a Lambertian sphere. So Johann Heinrich Lambert was a Swiss physicist, mathematician, and I guess philosopher as well in the 18th century, from Basel in Switzerland, not too far from here. And this reflection law bears his name, and in plain English, it basically says that one sees from a Lambertian sphere, one sees equal brightness in all directions, regardless of viewing angle. It doesn't take a sophisticated physicist to tell you that this is not very realistic, but it's easy to write down, right? So you can write down Lambert's law or Lambert's cosine law as stated on the slide. So the incoming intensity from the star, which is I sub star, hits the surface at some angle, theta star, and is then reflected at some angle I0. And the cosine law reflects what I just told you in English in the box. So this is nice. You can write down the expression for a Lambert sphere very easily. You can use it to compute all kinds of quantities. But is it very useful is the question. And it turns out that none of the solar system objects behave like Lambert spheres. In fact, if you look at, for example, the phase, if you first go to the top left, if you look at the phase curve of Jupiter, of Callisto, and Enceladus, which are the moons of Jupiter and Saturn, they look nothing like Lambertian spheres. And in fact, you will notice that the real phase curves have a very cuspy profile that is very sharp at zero phase angle. On the right, you see Cassini data taken in the early 2000s of Jupiter. And again, you can see that you can see this cuspy profile, and which is not consistent with a Lambertian sphere. There's even been Cassini data of Saturn's rings in the bottom, and once again you see that these phase curves of Saturn's rings of the reflected light of the sun do not look like Lambertian spheres, and have these cuspy profiles as well. We can talk about what these well, I suppose I could tell you, right? So the moon itself also has a cuspy profile, and this is called the opposition surge. And there are two effects that account for this. One is something called shadow hiding, and the other is something called coherent backscattering. We can chat in the Q&A if you like. So how about exoplanets? So what are albedos and phase curves? So from the phase curve, as I told you, is the flux from a planet of a moon as a function of the orbital phase angle. The albedo is the fraction of reflected light from the moon or the planet, but it turns out there are various definitions, as I mentioned in the beginning of the talk. So here's the jargon. I apologize for showing you a table, but this is a very old field, and the jargon is very well established. I don't want to invent jargon and confuse the literature. So I'm going to respect this jargon, and I will go through it with you. So the so-called geometric albedo, which you see in the graphic, the first row, and you look at the graphic on the right, is the albedo at 0 phase angle. So it's the amount of reflected light when you see the entire face of the moon, for example, right? So it's the albedo at 0 phase angle. The spherical albedo is the albedo considered over all phase angles. But at one end, the geometric and the spherical albedos are always defined at a single wavelength. The Born albedo is the spherical albedo over all wavelengths that's weighted by the intensity of the star. Another way of saying it is that the spherical and geometric albedo depends on the intrinsic properties of the scattering surface. So either of the atmosphere or the surface of the celestial body. But the Born albedo itself also depends on the so-called spectral energy distribution of the star. So if you took the same planet and you put it around a different star, say a M star rather than a G star, you'll get a different Born albedo. The phase integral, which I mentioned in the beginning of the talk, is actually the ratio of spherical to geometric albedo. And now you know why I didn't mention it, because it's difficult to explain it until you explain what the other two albedos are. So this is typically given by Q. And for example, if your scatterer if your scattering is isotropic, then Q will be 1.5, will be 3/2. The single scattering albedo is actually a very nice name because it tells you the fraction of light that's scattered in the single event. And I denoted by omega. So omega is the ratio of the scattering cross-section to the total cross-section that includes scattering and absorption. So most of the physics is how to relate the single scattering albedo, so the amount of light scattered in a single event, to the amount of light scattered macroscopically by the entire body. So how do you relate omega to the rest of these albedos is the problem. And now, if I once again put it in context, and especially in the context of exoplanets, you can, for example, read Sarah Seeger's very nice 2010 textbook, and you will see that if you measure the secondary eclipse depth of the planet in reflected light, so when the planet goes behind the star and you measure this really tiny dip in the light, then if you know the radius of the planet, which is r, and the distance between the planet and the star, which is a, these are geometric factors basically, then a measurement of the secondary eclipse depth basically directly gives you the geometric albedo of the exoplanet if you're measuring reflected light. More generally, you can measure the reflected light phase curve. So in addition to the geometric albedo given by AG and the radius r and the distance between the planet and the star A, there's a function called the integral phase function, which quantifies the shape of the phase curve. So in summary, if you find a way to solve for the geometric albedo AG and the integral phase function psi from first principles, which is done by solving the radiative transfer equation, then you have solved the entire problem. You can then describe all of the other quantities that I showed on the previous slide. Now I would like to give you a sense that that these quantities have existed in the planetary science literature for quite a while. So this is a paper from 1990, I believe. I can't see the entire slide properly. 1991 by Pearl and Conrath. And you can see, for example, that people have used Voyager data to measure and quantify the geometric albedo, the Born albedo, and the phase integral of Jupiter, Saturn, Uranus, and Neptune. So in this study, the the Born albedo of Jupiter was quantified to be about 34%. Then after the launch of Cassini in the early 2000s, this Born albedo of Jupiter was substantially revised upwards from 34% to roughly 50%. And this is, I just want to give you a sense of how beautiful this data is. So as I mentioned, the geometric albedo and the spherical albedo are functions of wavelength. So therefore, you can think of geometric albedo spectra and spherical albedo spectra, and this is what this slide is showing you. So in blue, this is the geometric albedo as a function of wavelength, directly measured by Cassini. In red is the spherical albedo as a function of wavelength, and the ratio of the two is the so-called phase integral, which has been mentioned before. So beautiful data of Jupiter. Will probably never get such beautiful data of exoplanets. How about for exoplanets? For exoplanets, there's a niche body of literature that measures the geometric albedos of mostly Jupiter-sized planets and mostly hot planets. So this has been done by the Kepler Space Telescope, for example, and more recently by the TESS Space Telescope, and also in Europe by the CHEOPS Space Telescope. I'm part of the science team of CHEOPS, and I think a few science team members are on the call. The broad big picture message that emerges from these studies is that most hot Jupiters are dark. They reflect roughly 10% of the light when they are showing their full phase to you. And this has been predicted in 2000 by a paper by Sudarsky et al. In 2000, like I mentioned. And the reason why hot Jupiters are dark is because at temperatures of 1500 Kelvin and higher, sodium is in its gaseous form, and sodium has a very strong cross-section, and sodium happens to absorb at wavelengths in the visible, and this makes the atmosphere of hot Jupiters dark, and the observations seem to be confirming this. To date, there are no trends with exoplanet or stellar properties. In the distant future, we could probably dream of having geometric albedo spectra of Earth light or even Earth-size exoplanets with the next generation of space telescopes. Certainly, if something like LUVOIR flies, LUVOIR is going to observe in reflected light rather than thermal emission. So some of these ideas will be relevant. So that's a little tour of the observations and the jargon. If you have questions, I'll be happy to answer these questions at this point. If not, I'll keep going on. So either you can ask them in voice or you can ask them in the chat. I'm happy to answer your questions. If I don't see any takers, I'll keep going on. Okay, thank you. I'll keep going on. So now I've given you a little tour of the data, and I'll give you a sense of the history of the field. I would like to now talk about the theory, not too much, so that you get a sense of what we were thinking about. So one way to talk about the theory is to show you the people whose work have really influenced my thinking. And to do this work, I had to read either papers or books of these people. So I already mentioned Lambert, who lived in the 18th century, and his Lambertian sphere model, which is still very influential in astronomy. Even on the CHEOPS team, we use Lambertian spheres to interpret some of our data. There's the work of Chandrasekhar. Chandrasekhar was a Nobel Prize winning Indian American physicist. He worked on a lot of things. He also worked on radiative transfer. And one of his fundamental contributions to radiative transfer theory is that he derived an exact solution for isotropic scattering in the so-called semi-infinite atmosphere. A semi-infinite atmosphere is not an atmosphere with an infinite spatial extent. Infinite refers to the optical depth and not the size of the atmosphere, meaning that the atmosphere eventually gets very opaque. The other person to mention is Viktor Sobolev, whom I personally describe as a Russian master of radiative transfer. He wrote a really deep and insightful 1975 textbook from which I obtained many insights. I encourage you to read it if you like radiative transfer. And there's a paper written by Hapke in '81 that has been very influential in my thinking of these solutions, as well, as I will describe to you. So in the subsequent slides, I'm just going to show you 1 or 2 slides from each of these people, and so that you can see the path towards our work. It's important to show you this, that our solutions didn't come out of vacuum, and they will build upon the work by these people. So I already mentioned Chandrasekhar, and I mentioned that he derived an exact solution for isotropic scattering in the semi-infinite atmosphere, and the solution depends on functions that he called, that were eventually called Chandrasekhar H functions. So on the slides, you see basically the definition of the Chandrasekhar H function. This is a mathematician's dream and an astronomer's nightmare, because the H function, which depends on mu, which is the cosine of the angle, involves evaluating integral that itself depends on the thing that you want to solve for in the first place. So it requires numerical iteration, meaning is somewhat slow, at least not as fast as we would like it to be. And so not very convenient to use for fitting data, for example. There's a small literature on H functions alone if you are interested. Hapke in '81, in a paper that's been cited more than 1,000 times, discovered, well, there were several things that were very influential about this paper, but one of the things that's relevant is that Hapke derived an approximate but highly accurate explicit solution to the Chandrasekhar H function. So instead of this mathematically elegant solution that you see in the first expression, Hapke derived a closed form explicit solution for H. And in one of the plots in the paper, which I reproduce on the right, he demonstrates that these solutions are quite accurate. The accuracy is roughly 1%. This gamma that appears in these solutions is just the square root of 1 minus omega. And if you remember, omega is the single scattering albedo. So this is very useful. While I was working on these solutions, one of the things that continuously puzzled me was, well, when I approached the problem, I thought, let's just think about single scattering. How does single scattering of light behave in a semi-infinite atmosphere? So I started working on this problem, and the geometry of the problem is described in the cartoon on the left, right? So you've seen this cartoon before for Lambert's law. So you have incident light from the star at some wavelength, I star, landing at an angle theta star, and reflecting off at an angle theta. And the cosines of these angles are given by the mu's, so mu star and mu. So when I started fiddling with the solution to the radiative transfer equation, I started getting this strange combination that you see on the right in the slide, right? I get these combinations of mu's where mu star is divided by mu star plus mu. And the reason why I say it's strange is because when you then use these solutions to derive the other quantities you're interested in, like the different albedos and the shape of the phase curve, this becomes very messy, and it's in some cases it's impossible to evaluate this analytically. So I thought, did I actually make a mistake somewhere? And why does this strange combination of quantities keep appearing? And so I started digging, and I realized that this solution that you see is very old. And in fact, you have to dig all the way back to 1888, during a time when it wasn't, these are not even conference proceedings, these are the minutes of meetings. So in the minutes of a meeting of the Scientific Academy of Bavaria in southern Germany in 1888, Hugo Seliger, who was the director of Munich Observatory at that time, actually already wrote down these solutions. So if you dig through the paper, and my German is not great, but I recognize the equations, you will see these combinations of cosines that I mentioned to you. And so this is then not surprising that this was subsequently called the Lomo-Seeliger reflection law that was also mentioned earlier in the talk. So now if I put everything together, the intensity of reflected light, including both single and multiple scattering of light, has a mathematical DNA that depends on many contributors, and that's the right thing to acknowledge, right? So it depends on, in the green box, the Lomo-Seeliger reflection law. In the orange box is a quantity that called the scattering phase function that describes the mathematical relationship between light going in and light going out. In the yellow box is Chandrasekhar's classic solution, which describes multiple scattering in isotropic multiple scattering in a semi-infinite atmosphere. And of course, this expression is friendlier to use if you use Hapke's approximate solution given on the bottom left. So all of these authors contributed to getting this solution. How about Sobolev? I mentioned Viktor Sobolev, the Russian master of radiative transfer. So what insight did I get from Sobolev? Sobolev realized that you can solve the problem in at least 2 coordinate systems. And there are at least 6 angles in the problem that you have to think of. Really, there are 7, but let's keep it simple. There are 6 angles in the problem. So this is the geometry of the problem. I apologize for the slightly busy slide. So you are an observer on Earth, given in green, and you're observing a planet or exoplanet, which is, you can see the exoplanet with the coordinate system built around it, orbiting a star. So one coordinate system is the observer's coordinate system. So from the observer's point of view, there's an observer longitude given by big phi in blue. There's the observer's latitude given by big theta in pink, in bright pink. And then there's the orbital phase angle given by alpha in red. So these 3 angles would constitute one coordinate system. The second coordinate system is the coordinate system that's local to the exoplanet. So imagine you're a little point on the planet given by this blue square in the figure. Then from the point of view of this blue square, there are also 3 angles, 3 different angles. You can have the local longitude given by small phi in brown. You can have the local latitude given by small theta in slightly less bright pink. And you can have the stellar zenith angle given by theta star in purple. And in principle, you can mix and match any of these 3 angles to get a coordinate system. But it's convenient to define the observer's coordinate system by the 3 angles I described to you, and the local coordinate system given by the other 3 angles I described to you. And these angles can be mathematically related to each other using spherical trigonometry, which is given by the expressions on the bottom left. And what Sobolev realized, not surprisingly, is that you could solve for different quantities of interest, geometric albedo, spherical albedo, and so on, in either coordinate system. And what I realized from reading his book is that you should, in some cases, you will get the answer either coordinate system you use. That's just physics. The outcome of the physics should not depend on your choice of coordinate system. But if you choose the wrong coordinate system, you may run into really, really messy algebra. So what I realized is that from reading Sobolev's book is that for some quantities you should do it in the observer's coordinate system, and in other quantities you should do it in the local coordinate system, which I'll try to describe to you. So the other insight I got from Sobolev is that all of the quantities of interest can be actually expressed in something he calls the reflection coefficient, or at least the English translation of the Russian book calls it the reflection coefficient. And the reflection coefficient is nothing more than the ratio of the reflected intensity divided by the incident intensity multiplied by the cosine of the incident angle. And let's call this rho, because this is what Sobolev called it in his book. And so, for example, the geometric albedo is an integral involving rho, as you see in the first line in gray. The dimensionless flux, which I call the Sobolev flux in honor of Sobolev, is also an integral, a double integral involving rho. And the reason why this flux is important is because the ratio of f divided by f0, where 0 means you evaluate it at 0 phase angle, is precisely this quantity called the integral phase function, which describes the shape of the phase curve. So it turns out that you want to solve for the geometric albedo in the local coordinate system, and you want to solve for these Sobolev fluxes in the observer's coordinate system. And if you do that, you can get an analytical solution. So I'm not going to bore you with the steps. I'm just going to summarize give you the executive summary of this paper. So using these insights from these different authors, we derive analytical first principle solutions for the geometric albedo AG and the phase integral phase function psi for any law of reflection. The problem was first posed by Russell in 1916, which I already described to you. I already described to you that these solutions have no tuning parameters, meaning that they could potentially be useful for extracting fundamental parameters from data. And I will try to demonstrate to you that actually, if you apply these solutions to very precise photometry, this is a much more powerful way of constraining the fundamental properties of aerosols than precise spectroscopy. Remember at the beginning of the talk, I told you the big picture point of doing all of this is to improve our ability to extract quantities from data, right? And one way of doing this is to reduce the confusion that's given by these aerosols. So before I show you data, how well do these solutions actually work? So here are some benchmarking calculations. So this is in green is our solution for isotropic scattering for spherical albedo. And then there's this classic study by Van der Hust from 1974. And you can see that they agree so well that the disagreement is smaller than the thickness of the line. And in fact, you have to blow up the difference in log to actually see it. Here's a comparison to a more recent study by Matsuha and Barros, who wrote down rather sophisticated treatment of Rayleigh scattering. And again, the comparison of the spherical albedo between our study, which is analytical, and their study, which is numerical, is not much larger than the thickness of the line, or comparable to the thickness of the line. Well, these solutions do fail because remember, the key approximation, and probably the only real approximation we took, is that we assume that multiple scattering is isotropic. So when you compare to this study from 74, where if you compare Rayleigh scattering and isotropic scattering, you do really well, like I already said. But if you choose scattering that's very asymmetric, then the solutions start to break down, not surprisingly, because then non-isotropic multiple scattering starts to become important. The last slide before the data part is, I just want to impress upon you that the shapes of these phase curves actually encode really important information on the reflection laws. So if you focus first on the panel on the left, when the single scattering albedo is 50%, meaning that each single scattering event reflects half the light, then you can see that the shapes of the phase curve are very different as a function of orbital phase angle, depending on which reflection law you favor. So potentially, for example, if you had good enough data, you could tell between Rayleigh scattering by molecules and say isotropic scattering by small aerosols in green. If your reflector behaves like a perfect mirror, which doesn't exist in nature, meaning that 100% of light is always reflected, then everything looks like a Lagrangian sphere, not surprisingly. So now I see something in the chat. There's a question that asks, do I have to consider the ratio of the amounts between two scatterings? The answer is no, because the solution naturally describes the ratio between single and multiple scattering in a way that doesn't require any tuning. It only depends on the single scattering albedo. So yes, so yes is in the solution, but no, you don't have to specify it. What are the implications for data analysis is the last section I would like to talk about. But again, if you have questions, you can ask them now. There's one more question in the chat. Okay, it's just a acknowledgement. Thank you. So I think this section is the one that will interest most people, and not so much the theory. So what are the implications for data analysis? Again, before I drown you in jargon, I would like to go through this again, right? So remember, the geometric albedo is the fraction, the albedo at zero phase angle at a single wavelength. The spherical albedo is the albedo over all phase angles, but again at a single wavelength. The Born albedo is the spherical albedo over all wavelengths. The phase integral is the ratio of the spherical albedo to the geometric albedo, and the single scattering albedo is the fraction of light scattered in the single event. So I wanted to refresh your memory because in the next few slides, I'm just going to use these terms like you know what they are. So let's go. So the first implication, which I am very excited about, and I think the members of the CHEOPS science team who are on the call are somewhat excited by it, is that it changes the way that you interpret phase curves. So of exoplanets. Well, not just of exoplanets, but in general as well. So the standard practice so far is you measure the light as a function, the reflected light from a planet as a function of orbital phase, and then you fit the shape and the amplitude of the phase curve independently, right? So you fit the depth of the secondary eclipse for the geometric albedo, and then you fit the shape of the phase curve with a series of sines and cosines. And of course, if you add enough sines and cosines, you always find a fit. This is not surprising. This is just Fourier's theorem. But the problem with that is that if you add an arbitrary number of sines and cosines and you manage to fit your data, it's not actually clear what the numbers in front of these sines and cosines actually mean. So you can't interpret it. With these solutions, we can think about it a different way, right? So the phase curve is really given by the product of the geometric albedo and the so-called integral phase function, psi, the shape of the phase curve. And now these quantities are not independent. So Ag and psi are given by fundamental parameters, which are the single scattering albedo omega and the so-called scattering asymmetry factor, which I will review for you in the next slide, G. So G describes how isotropic or asymmetric the scattering is. So instead of fitting directly for Ag and fitting for the shape of the phase curves using a series of sines and cosines, what you should really do is that you should fit for omega and G. And once you fit for omega and G, they determine Ag and psi as an outcome. So what is this G? So G is a dimensionless number between -1 and +1. And it describes to you how isotropic or non-isotropic the scattering is. So if G is 0, then the scattering is isotropic, it's equal in all directions. If G is +1, then it's mostly forward scattering. If G is -1, it's mostly reverse scattering. Rayleigh scattering is almost isotropic, but not quite. I'll show you an example for Jupiter at the end. So this is nice to describe, but actually G has a rather complicated behavior in wavelength. So this is an example of CO2 versus water ice clouds, ice particles, spherical ice particles. And these are calculations done by Daniel Kitzman, who is a senior researcher in my group, of G and omega as a function of wavelength. So for carbon dioxide ice particles, these are shown in red, and for water ice particles, these are shown in blue. So we were interested in this because we were modeling the atmosphere of early Mars in a separate paper. So now if you just focus on the top panel for G and you focus on the solid curves, you will see that at wavelengths that are shorter than 10 microns, so the top left of the panel, you will see that G is close, not quite 1, but close to 1, right? And this is not surprising because when you're scattering radiation that is less than 10 microns and you're a 10 micron particle, you're a large particle, right? You're large compared to the wavelength of light you're scattering. So so G is close to 1. Now, as you scatter light that's redder and redder, longer and longer wavelengths, you see that G drops from close to 1 to 0. So this is one of the important lessons in radiative transfer, which is whether a particle is large or small is not its physical size, but the physical size relative to the radiation. So a 10 micron particle that scatters ultraviolet and optical light is large, but if it scatters mid-infrared and far-infrared light is small, right? And this is shown by the solid curves in the top left. And now if you have 1,000 micron particles shown by the dashed curves, then it's not surprising that it always behaves like a large particle. The behavior of omega is a little bit harder to understand, and I can't give you a quick intuitive answer. But one of the things we take away from these calculations is that, for example, you notice that the omega is close to 1, at least for the 10 micron particle, at near ultraviolet and optical wavelengths for water ice. But for CO2 ice, and it drops like a rock in the infrared, but for CO2 ice, it stays very reflective, even at infrared wavelengths. So what does this tell you? This tells you that when you do radiative transfer for the Earth, you have to be very careful about the scattering of sunlight, but you have to be less careful about the scattering of infrared radiation, at least for H2O ice clouds. For CO2 ice clouds, you cannot do that. So for CO2 ice clouds, your radiative transfer method has to be good at both scattering sunlight and also scattering infrared radiation, because if you don't do that, you get the wrong answer for early Mars. So enough of the review of G and omega. The other thing I have to tell you about is something called I have to tell you about inhomogeneous cloud cover. So when there are several reflected light phase curves of exoplanets in existence, and one of the things that we notice is that it doesn't exactly peak at secondary eclipse. It peaks a little bit away from secondary eclipse in the westward direction. And there's a very nice paper in 2015 by Renyu Hu that basically demonstrates that this is a direct consequence of having a patchy cloud cover, so non-uniform cloud cover on the exoplanet. And we showed in the paper in 2016 that that having non-uniform cloud cover is not surprising. It's the direct consequence of having finite condensation temperatures. So the map that you see there is a simulated temperature map of a hot Jupiter. And basically in regions where you're very hot, then depending on the condensation temperature of the aerosol of the clouds, you don't condense. And in cooler regions, you condense. So you basically get an atmosphere that's not equally reflective. It's reflective in some regions and not reflective in other regions. And if you want to fit real exoplanet data, you have to derive a solution that considers non-uniform cloud cover. And one of the things we are very proud of in the Nature Astronomy paper is precisely that we derive pen and paper solutions for both the magnitude and the shape of the reflected light phase curve for non-uniform cloud cover. But this is hidden in the appendix. So this has allowed us to, for example, interpret there's a question. I'll answer that later, Nuno. So this has allowed us, for example, to reinterpret the reflected light phase curve of the hot Jupiter Kepler-7b. This is 4 years of Kepler data. This is probably the most famous reflected light phase curve of an exoplanet has come out of the Kepler Space Telescope dataset. And this phase curve has been studied and re-reduced and interpreted by many authors in the literature. So we did the same, except that because we have these novel solutions, we can extract these quantities that have not been extracted before for the first time. So for example, out of our analysis of fitting this phase curve with non-uniform cloud cover, we can derive not just the geometric albedo, which is about 24.5%, but we can derive the spherical albedo, the single scattering albedos of the dark and reflective regions. We can derive the scattering asymmetry factor G, which is consistent with 0. So it's consistent with isotropic scattering, meaning that these particles are small compared to the wavelength of light in the Kepler bandpass. And from that, we can derive the phase integral, which is the ratio of the spherical to the geometric albedo, at least in the Kepler bandpass. One of the things this allows you to do is that it allows you to derive also, you know where the atmosphere transitions from reflective to non-reflective, and you can extract a condensation temperature, and the condensation temperature is about 1600. So one of the nice things about this analysis is that you're getting extra information about the scatters in the atmosphere that you couldn't get before. So I want to end on data analysis of Jupiter. This is the other paper I mentioned in the very beginning. And I want to start by saying that there's a long-standing puzzle with this with the Cassini phase curves of Jupiter. So the Cassini phase curve were collected in the early 2000s. The data is so exquisite and the error bars are so small that basically you can't really see them, right? So if you look at the plot at the left of the plot, you will see the Cassini data in these little black dots, and you can barely see the uncertainties on the data. And because the data is so good, this has allowed various researchers to realize that you cannot fit standard phase curves with standard reflection laws to the data. So for example, the Lambertian sphere doesn't fit. This is already known. The Rayleigh scattering doesn't fit because it's not cuspy enough at zero phase angle. And the so-called Hennief-Greenstein reflection law, which is used a lot in astrophysics and planetary science, doesn't fit as well. And no one, perhaps for the reason that these solutions were not previously known, they have never been analyzed within a Bayesian framework for any arbitrary reflection law. But because now we have these solutions and we can put any reflection law we want into the solutions, we can actually analyze them quite generally. So the reflection law that I chose for this analysis is something that's used very commonly in planetary science. It's called a double Hennief-Greenstein reflection law. And what this does is that it allows you, it's a fitting function that allows you to describe both strong forward and strong reverse scattering. And this paper in '95 suggests that double Hennief-Greenstein reflection laws can describe scattering of light by irregular particles. Whether the reverse is true, I don't know. So you can describe irregular particles by double Hennief-Greenstein, but if the data is described by double Hennief-Greenstein, I do not know if this implies that the particles are irregular. So we can now fit the data. And so I give you one example at 0.5 microns at the top. You will see that the double Hennief-Greenstein does a pretty good job, right? Much better than what came before. You can fit the data using a Markov chain Monte Carlo package. I used the one by MC by Daniel Foreman Mackey, and this allows you to extract the single scattering albedo, the G factors for both forward and backward scattering, and the weighting between them, which is called F. And now, since we have 61 Cassini phase curves from 0.4 to 1 micron, we can repeat this exercise 61 times. So you can construct the aerosol properties as a function of wavelength, which you see in the bottom plot, right? So for example, the single scattering albedo is close to 1, not quite 1. And what is interesting is that it stays very high, close to 1. And then at roughly 0.9 microns, there's a sharp dip. And the reason why this is interesting is that this sharp dip coincides with the so-called with the methane absorption band, MT3. And it has been shown in previous studies, or suggested in previous studies, that there's strong absorption of methane in this band, which is probably why they designed it that way. And you can also see that the scattering, the G factors, goes more strongly towards 0 in this band, so that is more consistent with scattering by molecules than, say, scattering by aerosols. So it's quite hard to visualize this this plot on the left. So one other way to visualize it is that you can take the average of these aerosol properties and you can interpret it geometrically. So if I do that, you get the plot on the right, and specifically the curve in red, right? So whatever is doing scattering in Jupiter's atmosphere has the scattering profile described in red. If these scatterers were molecules that were participating in Rayleigh scattering, the profile would be in blue. You see this double lobe shape of Rayleigh scattering that's not quite isotropic, almost isotropic. And you can see that the red scattering profile is inconsistent with this blue profile, right? So you have a lot of forward scattering and a little bit of reverse scattering. So the conclusion of our study is that the aerosols in Jupiter's atmosphere are large. They are large because the G factors are now close to 0. They are possibly irregular because of what I told you about the double Hennief-Greenstein. They are polydispersed, meaning they are more than one size. If they were just one single size, then the G factor should decrease across wavelength, and we don't see that. It's inconsistent with Rayleigh scattering. Multiple scattering is important because the single scattering albedo is close to 1. There's a backscattering lobe that we can talk about in the Q&A if you like. And we do not know what the composition of these aerosols are. Getting the composition of aerosols is one of the hardest things that you can do. But we know from previous experience that you don't need the composition of the aerosols to mitigate the effects of their effects on the spectrum. So I'm done. Thanks for your patience. So the summary, here's the summary. We report the discovery of a family of novel ab initio closed form solutions for the geometric albedo and the phase curve shape. I hope I've convinced you that the shapes and amplitudes of reflected light phase curves encode really important information on reflection laws and the fundamental properties of aerosols. I hope I've at least have started you thinking, even if I've not convinced you, that precise photometry is potentially more powerful at constraining the properties of aerosols than precise spectroscopy. And one of the consequences of what we find is that a strong test of whether an atmosphere is cloudy or cloud-free can be carried out by asking if the reflected light phase curve is consistent with a shape that is given by Rayleigh scattering. And so this is one of the things we are thinking about as well. So thank you very much for staying to the end. I'm very happy to answer your questions.
Well, thanks a lot, Kevin. I have already a question by Nuno Santos on the chat, as you have seen. The question is, why large particles scatter forward and not backward? At first sight, it sounds counterintuitive to me.
Yes, I don't have an easy back of the envelope answer for you. It just comes out of me scatterings. So I haven't found an intuitive way to explain this. If you want, what we found is that if you want strong reverse scattering, you actually need for the particles to be charged. I don't have a better answer for you than what I just gave you. Sorry.
Okay, that's fine. Are there any other questions? So if you want to ask a question, either use the chat as the colleagues before, or you can also put on the video so that I can see you and can give you the word. Any further questions? Yes, there is. Just a moment. Jose, is this a question or is it just a comment you wanted to make? Yeah, there is a question of Jose Caballero around M-graph. We assume A bond is 0. Is it too bad?
I think in general, it's dangerous to make any type of assumption for the Bond albedo without actually having any information on the atmosphere. I guess that's my reaction to his comment. Well, the proper thing, you asked if there are any suggestions. What the proper thing to do is to just go out and take spectra of these atmospheres. And you can actually measure the Bond albedo just like we did for Jupiter, or at least you can estimate it.
Okay. Are there any further questions then? Please don't feel shy to ask. I cannot see anything on the chat. I cannot really see any.
I can see the chat is fine. Yeah.
Yeah, I cannot see anything on the chat. I can. There is also a though on nobody moving on. So I would like then to thank our speaker again and wish him all the best for his future in Munich. And I would also like to remind you that the next talk will be given by Nuno Santos on the 30th of November, same time, 4 o'clock. Central European winter time, and I hope to see you there again. For the rest, I wish you a pleasant evening, and thanks all again for coming.
Thank you for giving me 1 hour of your life. Bye-bye, everyone.